Hello and welcome to this video. In this video, we're going to be taking all of the things we've done so far. So we've looked at quarks, we've looked at leptons, we've looked at the exchange particles and the fundamental forces. We're going to bring them all together and show what this means in the standard model of particle physics. Okay, so we can take all particles. Okay, so this is how we're gonna separate all the particles that we know of into the standard model. This isn't the only representation you could find of the standard model online. You can probably find more diagrams, but to simplify things, I'm just going to draw it out like this. Okay, so all particles we split into leptons over here. Then we have exchange particles. And now the third one we would expect to call quarks, but since quarks splits into baryons and mesons, we can have both of them. Collectively, that whole group are called hadrons. Okay, so just as a side note, a hadron is basically anything that is made up of quarks. Okay, and therefore we know hadrons can be split into baryons, but also into mesons, like we saw in the quark video. Okay, so now that we've got all of the categories that we can sort things into, we can now look at what particles fit into these categories. And if you remember, with these leptons, we had 6 types of leptons. We had the electron, which we were familiar with. We introduced the muon. And the tau, but then we also looked at the corresponding neutrinos for each of these things. And I'm going to say here, plus all the antiparticles as well. Okay, because if we're involving all particles that exist in the universe, we know antiparticles exist in the universe as well, so we have to include those in this. But these are the ones that you would have to know. More specifically, you don't have to worry about the tau and the tau neutrino, but they're there because I feel like it makes more sense to have a complete set. Okay, that's leptons. Now, exchange particles we looked at in the fundamental forces video. And in that video, we went in order of the strongest fundamental force to the weakest. So that's what I'm going to do with the exchange particles again. I'm going to say the strongest are gluons. We also have the second strongest, which was the electromagnetic force, which has the exchange particles of photons. Then we had W plus, W minus, and Z naught. And then finally, we had a graviton. Okay, and these are your exchange particles. Okay, I will say at this point that sometimes we can call these exchange particles bosons instead, but I would try your best to refrain from that. I know boson sounds like a much more impressive name for them, but there are things in the mesons, for example, so pions, for example, are also bosons, but they're not in the exchange particles category. Okay, so a boson is defined purely by its spin, which is just another one of those quantum values that we'll look at, like something has a charge, something has a mass, a baryon number, it also has a spin, and so that defines whether it's a boson or a fermion, which is another way of looking at its spin. But for now, we're just going to call these the exchange particles, although these are all also bosons. Because not all of the bosons are in this list, we can't call the whole list bosons. But these are the exchange particles that we need. We don't have any antiparticles for them because we can't get the antiparticle of a photon or a gluon or anything like that. So these are just virtual particles that exist. We can't really get antiparticles of those. Now, hadrons, we looked at in the quarks video, and we said examples of the hadrons are the baryons and the mesons. The baryons we split, and we said we have protons and we have neutrons. Okay, now these we're very familiar with, right? We've known about these since like key stage 3. What we need to also make sure we know is the quark compositions of these things. So we need to know that protons are up, up, down, and neutrons are up, down, down. And those are the 2 examples of protons that you have to know. These aren't the only baryons that you're gonna encounter. There is the possibility that in exam questions they might ask you about other baryons that you haven't heard of, but what they ask you is just going to be to basically reconfirm your knowledge about baryons. So they'll ask you something like, what's the baryon number of this? And the way we calculate a baryon number is just if it's a baryon, it has a baryon number of 1, and if it's not, it has a baryon number of 0. Right? So it's basically just saying, is something a baryon? And we said baryons, the way we defined them was that we had 3 quarks. Okay, that's the general quark composition of a baryon, but we also said we can have the antiparticles of these, so it could have an antiproton or an antineutron, or anything like that. Okay, so I can have antibaryons. And then the last one over here is mesons. So mesons, if you remember, were a quark antiquark pair, and we had 2 examples of those, but they were split into each of them was split into 3 different types because we can have 3 different charges. So we can have kaons, which look like a K plus, a K minus, or a K naught, and then we can have pions, which are pi plus, pi minus, or pi naught. Okay, I'm not going to go through the quark composition of these because you can find those in the quarks video, but then I will go through the properties of these things. Okay, so what we said, kaons, remember, are strange. Okay, so I'm just going to put strange here. We have to know they're strange, and if you remember, we said because they're strange, they have an unusually long half-life. So this is the general understanding of our standard model now. So we have all particles are split into leptons, exchange particles, and hadrons, but hadrons then split into baryons and mesons. We have antiparticles of leptons, baryons, and mesons, but not of exchange particles. These are all of the leptons that you have to know, disregarding the tau and the tau neutrino, but again, we're including that just because it's good to have more knowledge. And then the baryons, you need to know protons and neutrons and their quark compositions. Mesons, you need to know kaons and pions. You also need to know their quark compositions, but I have already covered that in the quarks video, so you can go and watch that, and hopefully that will clear that stuff up. It's not too complicated. But along with this, I'm going to make another table for quarks and then a table for leptons, and then hopefully that will be the summary for all of the standard model. So let's make a table over here for the quarks. So we're going to look at what type of quark is it, what charge does it have in terms of E, the charge of an electron, what's its baryon number, and finally, what is its strangeness. Okay, so the quarks that we have to worry about, as I've said before, we only have to worry about up, down, and strange. We don't have to worry about charm, top and bottom, although they do exist. So I am going to write them here. So strange, charm, top, bottom, but I'm not going to fill in any information about them because it's not necessary that you know that information, so I don't want to throw in too much extra information to the point that it gets confusing. If you want to find out about those, you can pretty easily look up the information you want online about them. Okay, but what we need to know is that an up quark has a charge of plus 2/3 the charge of an electron, down is minus 1/3 the charge of an electron, and strange is also minus 1/3 the charge of an electron. Baryon number, they all have 1/3. And that's because if we think back to baryons, what I've said is that if something is a baryon, it has a baryon number of 1, meaning baryons are 3 quarks, so we should add together 3/3 until we get a total number of 1. If something's not a baryon, so i.e. has no quarks, leptons don't have a baryon number, so any, like electron, have a baryon number of 0 because leptons don't have a baryon number. But even mesons will have, so if you remember, mesons are quark antiquark, which means they'll have plus 1/3 for the quark, but then minus 1/3 for the antiquark, so they overall have a 0 baryon number. Okay, and then strangeness, up isn't strange, down isn't strange, but strange has a strangeness of minus 1. This table can be found in the formula sheet. Okay, this is everything that you need to know about these 3 quarks, and you can find that in the formula sheet. So this is the quarks table, then the leptons table. The one that you can find in the formula sheet is very limited. I'm not going to draw out that one. I'm going to draw out a slightly expanded one that's going to go through a little bit more information. So the leptons, we need to know their charge. Let's go in terms of the electron again. Now we've got lepton number instead of baryon number, and we don't care about strangeness, so we'll just care about charge and lepton number. We'll put this as the symbol, just like we did in the original video. Okay, so let me just get rid of this quark table, and let's go through this one now. So, so these leptons, we know we can have the electron, we can have the muon, we can have the tau, and we can have the electron neutrino, as well as the muon neutrino and the tau neutrino. Okay, these are all the leptons we have. Now the charges that each of them have, the electron is minus the charge of an electron, muon is also minus the charge of electron, and so is a tauon. We said the only difference between these three is their masses, essentially. They just get bigger masses as you go down the group. The charge of a neutrino, all of these are going to be 0. Okay, we can't have, if they're neutrino, they're neutral, so they have no charge. Lepton number of all of these things is 1. Because they are all leptons, so they have a lepton number of 1. As soon as they become the antiparticles of what they are, they become they have a lepton number of -1. But if you have something that's not a lepton, it has a lepton number of 0. Okay, this lepton number is what you find in the table in your formula sheet. So let me put a star here. So this is in the formula sheet, so you can find this. And basically, if they ever give you the symbol of a lepton and they ask, is this a particle or an antiparticle, or what is the lepton number of this, you can always look at that table and figure out whether it's a particle or antiparticle, or it's a what its lepton number is. Finally, the symbols for all of these things: electrons are E-, muons are mu-, tau is tau-, and neutrinos are all have the Greek symbol mu, but then nu, but they all have their own type of lepton, almost flavor of a lepton. And this is the standard model. So this is everything we need to know about all of the particles as a whole. So all particles, we have this whole table. This table, it would probably be best to be able to memorize. This is one of the few topics in physics where you actually do have to memorize the names of things. So you have to memorize the words like hadrons, baryons, mesons, leptons, exchange particles, what those things are. But in terms of like quark compositions, you can always figure those stuff out. It's that you don't have to memorize those. But if you are a memorization type learner, you can always memorize stuff. I would say that approach isn't going to last very long in physics. It is much more of an understanding and application-based subject. But for particle physics, you can get away with memorizing stuff for now. Then we looked at the table for quarks, looked at their charge, their baryon number, and their strangeness. And then we got the final one for leptons, and that is all of the particles that we're currently familiar with, that we're going to go through in A-level. Hopefully this will make sense. Thank you for watching.